Welcome to the general seminar this February month, given by Pascal RUELLO from the Institut des molécules et des matériaux du Mans, Institute of Molecules and Materials of Le Mans. So Pascal RUELLO made his studies in Rennes, where he took the magister de physique. And then he prepared his PhD at Central, not Supélec at that time. In the SPMS laboratory, so about materials and simulation and physics. And at the same time, the thesis was funded by CEA, so the French Atomic Energy Center. And it was about transport, so ionic transport, polarions in oxides at high temperature. You can guess which kind of oxides, and they're in relation to their structure. Then he was for a short time assistant, and he got a position as an assistant professor at Université de Mans. He made a stay at TU Braunschweig in Germany also for some time. Also, when he decided to study matter excited by ultrafast waves, he had 2 years of French system delegation, so a kind of agreement between university and CNRS when you can do full-time research. And for this, he was at Paris, at Jussieu, in the ENSP, the group led by Bernard Perrin, who are pioneers of this technique. And so he developed he worked there on a pump probe experiment at low temperature, studying the metal insulator transition in nickelate. And since 2002, he has set up a group which keeps on growing using pump probe techniques at Le Mans University, so about molecular materials. And initially, he worked on the type of phonons which are generated. So you will have lectures about phonons. And now he's expanding to spectroscopy related topics. So thank you, Pascal RUELLO, for accepting, and please.
Thank you. Thank you, André, for kind introduction, and thank you for the invitation to give this seminar at LPS. So thank you for coming, and thank you for people who are connected to Zoom. Everything works well. You can hear me. You have to solve that technical issue first. Still, it's very sensitive. Maybe I can take the other one. That's okay. Oh, yeah. Can you? Does it work properly? Yeah. So no more noise. So thank you for for help in solving that issue. And for me, it was not so uncomfortable, but I imagine for you it was. So I will go on with English, yeah, if everybody is okay. So thank you again for the invitation. So today we like to give you, just kind of overview about generation of phonons, and I will focus mainly on the acoustic phonon. So generation by light. So we will, of course, discuss the regime of which is called ultrafast light-induced current phonon generation. And I will give you some example for the situation we can meet in semiconductors and ferroelectrics for a couple of samples. So as André told you, so I work in this CNRS lab and university lab in Le Mans, so Institute of Molecules and Materials in Le Mans. So for people who do not know where is Le Mans, it's, let's say, 1 hour by train far from Paris. Yeah, if you want to go to the sea, then you maybe across Le Mans station at one point in time. So that this is a couple of pictures of Le Mans if you do not know. So a nice small city. So the lab where I work is a laboratory where there is there are chemists, also material scientists, and I work in the department of physics, and I will mainly discuss the activity that we developed in that first direction, where we look at the coupling between the electrons, phonons, spin, and so with different techniques, but I will, of course, focus on the ultra-fast time scale. So these are my colleagues that are involved in this research direction. So recently, Lucid joined us as senior position, and Marwan as a chair professor junior. And Mads 2 years ago arrived and to develop experiment with second harmonic generation. And Vincent leads the THz setup, and Gonel is a research engineer that takes care about all the laser, and we interact with Brice Arnaud as well for the theoretical part. So this is just a short picture of our equipment. So we will not details all what setup we have, but just a few words about that. It's tell that we have different wavelengths for pumping or probing, so in the visible range, the infrared range, but we have also THz experiments. So we can cover, I would say, from the milli EV up to couples of EV. So when we look at the interaction between the light and solids. And we recently joined the what we call infrastructure, Ultrafast in the case of PEPR, LUMA, which is a Lumière Matière, organization for the France 2030. Okay, so these are first a couple of acknowledgements. So the experiment I will describe today have been carried out thanks to couples of collaboration. So from colleagues here at Claire. And we also have collaboration with people about ferroelectrics that they provide us samples. So we do not grow samples. So we study different samples, but that are provided and characterized by colleagues also from Central Supélec as well, or DCA. So this is the outline of the seminar. So I will give you a few words about the introduction, why we are studying phonons, why it's interesting. And then I will detail a bit more the photo generation process as well as the photo detection. So how we can generate phonons, how we can detect them. And I will give you a few examples in semiconductors, in let's say ferroelectrics, multiferroic materials, or also in superlattices. So as I told you, so this seminar deals with ultra-fast dynamics. So this picture, which is adapted from that paper, so you can find lots of different pictures like that, just telling you about what kind of mechanism or what is the typical characteristic time which is involved in the different mechanisms. So of course, we will mainly focus on the solids, so we will not discuss molecules. So for solids, typically the time scale I will discuss today is, let's say, the picosecond time scale, where you have typically the interaction between electron-phonon. You have also some interaction between the phonon and magnon. So this is a typical time scale we will discuss. I will not discuss attosecond regime or the nanosecond or microsecond. So I will mainly discuss that picosecond time scale, which is really the scale where electrons and phonon interact. So this is typically, as you also probably know, the lifetime of such situation when you excite electron with, let's say, resonant excitation, with, let's say, interband excitation. So typically the lifetime of such carry usually is around, for intraband, let's say, relaxation is typically one picosecond. And during that time when electrons are excited in such conduction band, different processes can take place. So if there is an electric field, the electron can be accelerated, but these electrons also relax to emit according to different processes. So they can emit optical phonon and acoustic phonon. So this is what I would like to discuss with you today and to give you a couple of examples. So a few words about phonons. So all of you know the lattice dynamics. So this is the typically equation you certainly saw and play with during your studies. So this is typically for 2 atoms per unit cell. So if you generalize that as 3-dimensional, you have such what we call branch. This is acoustic phonon branch. This is the optical phonon branches. So this is the typical displacement for longitudinal acoustic one, longitudinal optical one, and this is transverse acoustic and transverse optical one. So there is a nice picture I found recently. So this is that's for students. It's sometimes useful. So this is basically how phonon move, how atoms move for the different branches. So for acoustic one and optical one. So here, basically, we used to say that optical phonon are motion in the unit cell, while acoustic phonon are just coupling between different unit cells. So that gives rise to the propagating properties. Here, this is the group velocity, which is nearly here a constant, which is sound velocity, while usually we used to say that it is more or less flat, let's say, that the group velocity is very small. So we used to say that optical phonon do not really propagate. So today I will mainly focus on these kind of phonon, which are the acoustic phonon. And the question is how we can generate them with ultra short light pulses. So of course, phonons, you are probably familiar with phonons when you look at what we know as inelastic light scattering process, like inelastic spectroscopy, like Brillouin and Raymond. So here, like what André and his colleague are doing. So Brillouin scattering is based on the inelastic collision between photon and phonon. So you have the Stokes and T-Stokes that you can get by the proper spectrometer. So these are what we used to say, we call them incurrent phonon, in the sense that they are, driven by the thermal bath. Yes, the statistics. In that case, Bose-Einstein defined the probability to find such a phonon. But in our case, what we discussed is that situation. We finally use a light. Yeah. So there are different kind of processes. So we excite electron, etc. And then by different mechanisms I will discuss, we can emit such a phonon. There are such a given relation in phase for all these phonons that gives rise to a packet, wave packets of phonons. And we used to say that these are coherent phonons. Of course, we generate them with light, and we can detect such a phonon by different techniques, let's say visible or range or X-ray diffraction, photoemission. So also electron diffraction can be used to probe this phonon. And as I will discuss sometimes, you can generate lots of things, but you usually do not see everything. Typically, this depends a lot on how you look at what the, it depends on how you can see this phonon. Sometimes you just see a part of this phonon that you have generated, the same way that you do not see all the electron dynamics you can trigger by the light. So everything depends on how you probe the system you have put out of equilibrium. So a bit of history, as you know, the main mine in the 60s, so after the laser, quite immediately, people used laser to look what happened on solids, and they immediately observed that there are some waves that are emitted. So they generate acoustic wave, different vibration in solids. So the first experiment, I think it's come from the 60s, yeah, from White in the US. And so at that time, so they understood that they were able to try to trigger some lattice motion with the light as soon as the laser were enough intense. And during the 80s, with the development of laser technology, and in the 90s with the titanium sapphire laser, everything accelerated. Yeah. So and lots of important paper were published at that time where they explained how we can generate current phonon with light pulses. And so this the group of Maris and Keith Nelson at MIT, and also the other group of the Dressel House as well. So they look at the theory of the generation of optical phonon as well as acoustic phonon. And also from the Russian point of view as well. So laser optoacoustics was developed at that time. So basically, for people who are not familiar with pump probe experiment, how does it work? We have a pump laser that excites the solids. Of course, there is electronic excitation like that. How we can detect them? We generate something here, we excite the solid, and with a delay probe, yeah. So typically by moving a delay line, so 1 centimeter at 33 picosecond, we record how the probe Yeah, so the intensity which is reflected as a function of a delay. Yeah. So we can reconstruct as a function of time how the optical parameter, because everything is built on the basis of the transient of the dielectric response. Yeah. So we look at how the reflectivity changes as a function of time, and then we can step by step reconstruct the dynamics. Of course, in such a signal, there are different things. We have such in the initial part, usually the first and very the first response is the electronic response. I will give you a few words about that a bit later. And after that, there are different dynamics you can trigger as a phonon. So why we're interested in phonons? How we choose this? There are different motivations. So first of all, with light, if you can generate phonons with, let's say, high frequency up to terahertz, means that you can control with the light the motions in a solid. So, and as you will see, we can also get direct access to electron-phonon, because with light you can control the population of electrons. So then, if you look at how phonon, what kind of phonon you have generated, you can discuss in more direct way which mechanism is involved in the emission of phonon. Of course, this is something that we will not discuss, but you can look at the phonon lifetime as well. And then in that case, you can directly measure in the time domain the lifetime of the phonon. What else? Of course, as you know, for phase transition point of view, phonon, if there is some, let's say, basically the soft phonon Landau approach, for example. So when you look at phonon spectrum, so the phonon you have emitted, if that change as a function of temperature, that can give you also information about the instability of the structure, so related to the phase transition. Of course, something that I will briefly discuss, acoustic phenomena can be used because they propagate this, so they can use to interact with other in the solids, like a magnetic order or excitons or ferroelectric polarization, for example. And of course, you can use as a light-driven actuator. Sometimes phonons are interesting because they can propagate in metals. Yeah, so in opaque materials where light cannot propagate, sometimes it's interesting for imaging. That's why people are working on that as well. And and the phonon is directly also to the bond stiffness. So when you use such current phonon, you can make nano-object vibrating, and then you can come back to the elastic properties of these nano-object. So basically, just to remind you, the typically resonant frequency of an object is roughly the ratio of the sound velocity divided by the characteristic dimension. So rapidly, if you work in such very small nano object, you jump rapidly in the hundreds of gigahertz up to terahertz frequency range. So, and if you want to develop, let's say, light-driven actuators, so you have to understand how you can convert light energy into mechanical energy. So this is typically to make some photoactuators, phototransducer, or photo-driven typical workers. So there are different, questions about that problem. So basically to go in that region. I did not mention that, but this is typically when you reach such high frequency, you can have waves, say phonons, with such a wavelength. So you can go down to the nanoscale. So a couple of papers just discuss how with this coherent phonon we can probe not only the elasticity, but also thermal properties, so phonon propagation, phonon lifetime, etc. So these are papers just copy here. So, and this is also what we can do. If you are able to make such a particle vibrating, you can probe directly van der Waals interaction. So this is typically what people are also doing now. So remember the picture I mentioned before. If you shine light, you make a nano object vibrating. And if you look at the vibration on the surface, you can come back to typically you can measure directly, finally, the van der Waals bond stiffness. So this is from the application point of view. You can use also phonon to make imaging, something I will not discuss today, but you can make what we used to say nanoechography somehow. It's basically the same idea that the echography that you know, but since you work with a high frequency, you can go down to very small spatial scale. From the physics point of view, as I mentioned, phonon spin and phonon magnon interaction is something very interesting as well, because you can modulate the, let's say, magnetocrystallinity in a system. You can, of course, play with the exchange and interaction by moving atoms as well. So, and if you pump phonons specifically, you can undo some switching of the magnetization. This is quite recent paper. So there are different situations where phonon can be used to drive magnetic properties, so magnons in different situations. So there is a recent review about what we call magneto-acoustics. As well, you can play with électron-phonon and exciton-phonon coupling. As you know, I will tell you a bit more later what is deformation potential, but with a strain, since strain can modulate the bond distance, so the interatomic distance, so you can change it's the overlapping, so the overlap integral, so you shift the energy of the electronic level. And then typically here, this is the exciton, the bond that shift as a function of time here due to the phonon. So you can play with electronic level with this phonon, and also just for, let's say, basic physics, but also to come back from that case, for example, to deformation potential parameter. So, but I will tell you a few words about what are deformation potential now in that part where I would like to come back to the physical mechanism of generation of this phonon. So after this, a couple of slides of introduction to show you that, of course, as you know, phonon can interact with many other particles in the solid. I would like to come back to the photogeneration and photodetection process. So basically, if you want to induce phonon motion, I mean atom motion, this is a basic oscillator equation. You have to induce a force with the light. And said differently, a force can be viewed, of course, as just a gradient of energy. So you have to induce, or gradient of the density of energy, or gradient of stress, as I will explain. So this is what you need to do. Here it is in the green, these are the unit cell of atoms. So if you want to generate optical phonon, you have to modify the distribution of energy in the unit cell. If you want to generate acoustic phonon, you have to induce gradients, and mean just you have to modify the coupling between the different unit cells, which is exactly the essence of the symmetry of motion of an acoustic wave, acoustic phonon. So if you take into account this oscillator equation, of course, if you want to generate phonons in the Fourier domain, you need to have such a Fourier component in your force, of course. And this is, of course, possible only if there is a spectral wave which works at that frequency. Of course, if you take typically 50 femtoseconds laser pulse duration, you can spread nearly all the entire frequency here. So, so typically, this is the case of gallium arsenide here. So 10 THz is roughly 30 millieV. So with such a femtosecond laser, you can cover all the frequency range of phonon. But this does not mean you generate all phonons, because it depends on the kind of the mechanism you have to deal with. There are some symmetry principles as well. But for the Fourier component, it is possible. So light-induced phonons. So there are two phonons, as you know, from the optical point of view. I will just tell you a few words, but I will mainly focus on that part after that. So there are different scenarios. Of course, as you know, with optical phonons, there are possibility to couple directly light with phonons, which is not the case for acoustic phonons. So it's indirect process. For light, for THz, you can have a direct. It is possible to have resonant interaction with a transverse optic phonon, for example. And of course, there are also a Raman. So for optical phonons, so this is the most direct, which is quite recent, because now we have THz, or large, or enough intense infrared laser that can give rise to such, coupling, direct coupling between THz electric field with infrared active mode. So this is possible. And as you also know, with visible light, with the stimulated Raman, you can, so when you typically pump below band gap, you can still, even if you work with virtual state, you modify the electronic cloud, and you can you still polarize the system transiently, for sure, but you can, in that case, through the Raman tensor, generate optical phonons. This is basically the case in that titanium oxide material. If you have above band gap excitation, then you create electron-hole pair. In that case, there is, let's say, what the people call displacive excitation of current phonon, or it's related to the deformation potential. You can generate as well optical phonons. So depending on the situation of the excitation, below or above band gap, or if you have turrets, you can generate different optical phonons. Yeah. Basically, you have, in that case, it's infrared active phonons. And in that case, usually you have AG, which is usually most of the time the symmetric Raman active mode in that second case. But you can have also EG mode. But I will not detail this too much. And regarding to the situation of acoustic phonon, as I told you, so for optical phonon, you have to modulate, you have to induce a force in a unit cell. And for acoustic phonon, you have to push, you have to induce a gradient. Acoustic motion is just what? It's a symmetric displacement of atoms, neighbors atoms. So that situation you need to induce what we call similarly a gradient of pressure, a gradient of stress. So this is basically, this is what is the blue line, I forgot to tell you. It's typically the light absorption. Yeah. So usually in a material, if you have above band gap excitation, light penetrates over a finite distance. So this is typically the profile of the light absorption. Yeah. And so that gradient, typically, that can be the gradient, of the light absorption, but the electron can move as well. So, but there is always a gradient. And this is a key element for generation of acoustic phonons. So basically, the photo-induced rays, which is like a photo-induced pressure, is usually first described by such expression, which is here just the profile of the light penetration. So, yeah. That's, I will tell you. Okay. Yeah, exactly. Yeah, behind that sigma zero term, there are different kind of mechanisms you can find. Yeah, there can be heating, there is deformation, but this is exactly what I will explain. Yeah, exactly. So if you are not so far from the, not so far, over quite large range of wave vector and frequency, the wave equation works quite well. This does not work if you are on the edge of the Brillouin zone. But even up to the terahertz, the wave equation works pretty well for describing the lattice dynamics of coherent acoustic phonon. Yeah, and this is classical equation. This is just quantum one. Here it's the interaction. How we can convert light into mechanical energy in a pressure. This is what I'm going to explain. So in such a situation, so we can, depending on the material, of course, you can sometimes generate both optical phonons like that and acoustic phonons. You see the two different frequencies. So, but what is very important for acoustic phonons to generate such a gradient of pressure. Yeah. So, of course, you can recognize in such equation the classical equation. Everything written like that is classical, except the fact that the sigma, is a quantum one. Yeah. So this is what I will discuss. I would like just to remind you that you can also induce motion by light by what we call the radiation pressure, as you already know. But in our situation, it is negligible. Yeah, it's negligible. You can put numbers and you can find that it is negligible. This has been well discussed quite recently, that paper. So this is a situation I'm going to explain. So to answer to your question, this is exactly due to the generation of acoustic wave, acoustic phonon is perfectly, entirely controlled by the gradient of the light absorption in the case of light absorption. So this is what, there are different mechanisms. So this is what I told you. This is quantum one. This is a quantum of quantum origin. And this is what I will explain. So just to remind you, this is the general case for tensor expression. So, and if you come back to that equation, you can solve it. It's linear partial differential equation. So in that case, it's just still linear. So you can solve quite immediately. Of course, this can appear as a bit complex, but basically this is the absorption profile. Yeah. And what is emitted in the space as a function of the depth here. This is typical what we call the bipolar pulse. So when you shine light a solid where the light is absorbed, this is exactly what you have in the solid. So there is still I would say a static part can be used, let's say heating or long lifetime carrier, depends. But what you emit, this is typically that situation. It's a bit different that sometimes the picture have. If you shine light on the solid and you excite optical phonon, you do not think about the space dependence because you say, okay, group velocity is nearly zero of optical phonon. So it does not, we just have in mind the temporal dynamics, but not the spatial dynamics. But for coherent acoustic phonon, it is crucial to understand not only the time, but also the space dependence of the interaction. So now behind, so this is just, we just play with wave equation here. We have a wave equation, we have a gradient of a pressure, but what is behind? Yeah, what is behind such a photo-induced rays? So these here are the time to discuss the different mechanisms. So a few words about that. Yeah. So if you make, in that case, of the general expression of that bipolar pulse, you make Fourier transform, and this is a spectrum. Yeah. And this is very important because for optical phonon, if you can couple the light with a given branch, then you say, okay, I just excite that longitudinal optic phonon. That's all. Okay. But for acoustic phonon, this is the branch. Yeah. So depending on how the light energy is absorbed, how the light energy is converted in mechanical energy, the spectral you emit can be very different. Sometimes you can reach rapidly THz, sometimes not. It depends on how the light is absorbed. Basically, here, smaller, yeah, the key term, yeah, and larger the phonon frequency. So this is just the discussion about the spectrum component. But I still did not yet discuss the physics, yeah, what is behind the sigma zero term. This is what I'm going to explain. But this is important to discuss that spectrum because usually when we shine light, as I told you, what do we excite exactly? It depends a lot on the way you describe the change of the photo-induced stress in that case, or photo-induced stress is equivalent of the force you induce on the atom's position. So if you come back to the thermodynamics, there's a relation between pressure and energy. And this is just a convention. Yeah, the stress is the opposite of the pressure. But when you shine light, you can shine the electron energy. You can shine the phonon energy. You can shine the spin, etc. So as soon as you change E, yeah, you can induce the pressure or the stress. This is exactly what happens in the light matter interaction. So deformation potential for people who are not familiar. Basically, if you are at thermal equilibrium, you are that situation. But if you shine light, you somehow put electron in different conduction band, for example, different valley. Yeah. So as soon as you do that, finally you change the distribution of carrier, and this will immediately modify the interatomic potential. In that case, so the potential of the materials has shifted. Yeah. So what is very important that for deformation potential, you can induce different kind of pressure. Basically, if you shine light on silicon, it will contract, yeah, just because of the deformation potential. It's as if finally you can excite carriers in bonds that are bonding or non-bonding, for example, or anti-bonding. Yeah. So depending on how you populate this electronic level, you can induce then finally different. You can have different consequences on the lattice volume, yeah, or interatomic distance. You can contract or you can expand.
In our next group meeting, Gabelli present.
So the stress, yeah, is related to the modification of the electron population or at that energy level, and this is what we call the Gröneisen electronic Gröneisen coefficient. So you can write it that way as well. This is related to the derivative of energy level according to the strain. Here it is a strain in the sense of the mechanics for acoustic phonon, but you can have the same thing for optical phonon, where the strain is just in that case limited to the unit cell. Yeah. And for metals, you can also show that if you modified the electron energy of the, let's say, of the Sommerfeld of the Fermi sphere, you immediately induce the pressure, which is electronic pressure. Just tell you a few words about that. This is a two-temperature model. I don't know if people are familiar with that. So when you shine light on such metals, for example, you put electron in high energy level. And so the electronic temperature, the equivalent of temperature, is very different. Yeah. So people use the two-temperature model, so the huge change of the electronic temperature. So by electron-phonon collision, electron relax, and then the energy is converted to the lattice subsystem. But during that time, yeah, where electron, the hot electron, still exists, there is that negative, yeah, stress, which that the pressure just because it's as if the Fermi sphere has expanded. Yeah, this is electronic pressure. Yeah. So that can, if you put 1 eV per electron, for example, you reach the gigapascal. It's very important. So this is what we call electronic stress. And for semiconductor, for gallium arsenide, if you shine light, if you put electron in that, let's say, zone center, or if you put electron in the X or L valley, the deformation potential is different. For example, if you put electron hole in that here, just above the band gap, this has been measured by different techniques. The deformation potential in that case is positive, so you induce the expansion of the semiconductor. But if you shine light, for example, in the X valley here, yeah, okay, the solid must contract. Of course, there is intervalley, which is very fast, so usually to see that, according to me, does not be observed yet. Yeah, but it is expected that if you shine light, if you populate that valley, you induce the contraction of the solid. So the deformation potential is one mechanism. Thermoelasticity is something that people asked about a couple of minutes ago. It's just due to the thermal expansion. Of course, when you shine light, you excite the electron here, so they come back step by step by electron-phonon emission. I mean, by phonon emission, electron-phonon coupling. So if you have such transfer of energy from the electronic level to the lattice level, it means you increase the vibrational energy. So as soon as since all lattices are harmonic, yeah, so average positions, as you know, it's thermal expansion. So in that case, if you have thermal expansion, which is beta, in thermodynamics, it's related to variation of the pressure. It's simply what we call the phononic pressure, phononic stress. And this is exactly in the Sommerfeld model, what you can compute. Yeah. This is the stress induced by hot electrons is very short time scale because the electron lifetimes is very short. But the heating can last a long time because it's just limited by heat diffusion. So these are typical, the sketch of the photo-induced stress in metals induced by hot electron, and by phonon, which is so-called the thermoelasticity. So, and the last mechanism I would like to discuss today, this is piezoelectric effect. What is piezoelectric effect? It's basically something that happens in all non-centrosymmetric material. So as soon as you have an electric field, yeah, in such non-centrosymmetric, if you modulate that electric field, you can induce a stress or strain. Yeah. So basically this is that situation. If you shine light in a system where there is a pre-existing field, if you put electron and electron and hole pair, you can screen that electric field. In that case, the lattice just relax and emit phonon. This is the inverse piezoelectric effect. This is what people know in transducer, piezoelectric transducer. But in that case, as I will show you, we can trigger it by light, by injecting electron hole pair in some depletion layer of semiconductors. So basically, a short summary of all mechanisms we can have. Basically, this deformation potential works well for semiconductors, thermoelasticity for metals, piezoelectric, of course, of piezoelectric material, etc. So depending on the materials you have, you can induce coherent acoustic phenomena with different mechanisms. So let me show you, tell you a few words about the detection. Of course, once you have generate phonons, yeah, how you can detect them. Basically, there are two situations. If you still work with, let's say, optical pump probe, phonons usually modulate the refractive index. Yeah, this is the photoelastic effect, which is so-called the Brillouin, or the same thing for if you have optical phonon, you have the Raman. So motion, I mean, atom vibration modulate the dielectric constant. And if you modulate the dielectric constant, you can get the information through the optical parameters such as reflectivity or transmission. Yeah. For X-ray, you can also, by using the Bragg law, you can immediately measure how the lattice distance and interatomic distance change by recording, let's say, the interatomic distance with Bragg law, X-ray diffraction. So I will also show you one example about that. So let me come back about the phonon spectrum. This is what you can emit with light. But sometimes with Brillouin spectroscopy, you just see only one frequency. Sometimes you can detect lots of things, but you detect one thing. Why? It's like that. Just let me remind you the basic detection process. So this is the sample, phonons are generated here, and this is the light that comes back to your detector. So the light is first reflected. So this is the reflected part of the light. This is the electric field. And there is a scattered one, which is proportional to the incident. And it is modulated by rho, which is smaller than 1, of course. And this is a change of phase as well. And that change in intensity and phase is just related to what? Just to the convolution between electromagnetic field, which is scattered. This is the transfer momentum of the light, and convoluted by the strain here, just for the acoustic phonon point of view here. Yeah, current. So, and this is, you have to make integral. Since phonon can be here or here or here, you have to make the integral from z to 0 to the infinite. So this is what you can get. And if you are interested in the reflectivity, you have to take just a real part. And this is that integral that characterizes the detection point of view. If this strain can be developed in a Fourier space here, and then from the optical point of view, you finally get such integral to be solved. But take care about something. If the refractive index is real, it means you probe below band gaps. You look at transparent material. In that case, the wave vector of the light is purely real. And that integral just is simplified to the Dirac function. In that case, you come back to the what we call the Brillouin oscillation, and you detect only one oscillation typically like that. So in that situation, we excite gallium arsenide, and we see only one single frequency. But we know that we generate lots of different things. But just because of the detection, we see only one thing. So we used to say this narrowband detection. And if in that case you have the same integral, but this is, in that case, you have an imaginary part, it means you probe the phonons in an opaque material. So basically, you probe above band gap. So you cannot do something else than solving that equation, doing the calculation. In that case, you can probe much higher frequency, and you are in a broadband detection. So you have different situations. So when you see a signal, if you see something oscillating, you say, okay, I see phonon, nice, but take care that you just see something, only a part of what you are generating. So let me show you 3 examples now. So first about the piezoelectric semiconductor. I will show you that we can, with light, we can induce compression or expansion. We can even stop the lattice motion with the light. I will show you just by playing with the competition between 2 kind of electron-hole acoustic phonons, which are deformation potential and piezoelectric effect. So first of all, I discuss that situation. We have a semiconductor, which is p-doped in that case, and there is a built-in field in the surface. Just basically, majority carrier are trapped, and there is a built-in field present on the surface. And in that case, as you know, the piezoelectric effect, it means if you modulate the electric field inside, you can have positive strain or negative strain, yeah? Depending on how you change the electric field. So in that case, this is a typical sample. You can buy it. It's a 111 direction gallium arsenide, but since it's piezoactive, the phase B and the phase A are not equivalent. What does it mean? It means finally you can induce either compression or expansion of the lattice, depending on the side you shine light. So if you are on the phase B, for the phase B, when you shine light, so this is typical, the typical band structure of the thermodynamic equilibrium. When you shine light, let's say above band gap, you probe with, let's say, a red of 800 nanometer. You do pump with 400 nanometer. So you create electron hole pair here near the surface, and basically these electron holes are accelerated in that built-in field and screen that field. Yeah. So if they screen that field, in that case, through the inverse piezoelectric effect, force the lattice to relax from a mechanical point of view and emit just coherent acoustic phonon pulses. If you do the same thing, but the other side, in phase A, that case, you have the same thing, but in that case, the strain pulse is the opposite sign. Yeah. So the consequence is what? If you look at the detection, in that case, we are in the Brillouin geometry, in the sense that we probe nearly below band gap, and we just detect a single component of the strain pulse. And what do we see? Finally, you shine light, we see, we excite, there is an electronic signature first, and after that, we see oscillation like that are typically the coherent acoustic phonon. And if we look at the signal on phase B or phase A, they are opposite. It's just due to the fact that the piezoelectric effect can be reversed. You can control compression or expansion. And I would like, so with the light, you can really control the lattice motion. Typically, here it's the optical penetration of the pump is 20 nanometer. So we control the light motion within the first 20 nanometer beneath the surface. So let me show you another situation with the Denver field. Denver electric field it is something that works well in undoped semiconductors. So there is no band bending on the surface. And when you shine light on the such semiconductor, due to the fact that the effective mass of electron and hole are different, diffusion coefficient are different. So electron diffuse more rapidly than hole, and then it creates what we call the Denver electric field. And this Denver electric field is related to the diffusion coefficient and the mobility. So in gallium arsenide, we can typically reach such electric field, which is 10 kilovolt per centimeter. And then we look at typically the current acoustic phonon emission through the Denver effect. We have such a sample like that, and we shine light on one side or the other side. Yeah. And if you look at the theory on phase B or phase A, so when you shine light, you create a Denver field. But these directions are non-equivalent because this is a non-central symmetric material. So in that case, you create a positive electric field, so they have a positive strain. In that case, you create a negative electric field. Yeah. So according to that z-axis, so you induce compression. So this is exactly what you explain, what you expect, expansion, compression, and exactly what we observe. We did such experiment. We shine light, this creation of Denver field, and we probe by Brillouin as well. Yeah. So we look at how this Brillouin changed as the function of the pump power. So look, this is a low power, so we increase and we see oscillation amplitude increasing. Okay. And when you plot it, it looks like that, the red part. Yeah. But if you do the same thing for the phase A, you see the oscillation. It increases, and after a given power, the amplitude nearly vanish. And then again after that. But there is a phase, a P dephasing that occurs. And if you plot just amplitude, you have things like that. Why it's like that? It's simply because in such a situation, in the undoped semiconductor, there is two kinds of photo-induced stress. There is a deformation potential, which is in the case of semiconductors always negative. Yeah, it means you create electron hole pair, and this induces expansion of the lattice. But depending on the phase you are, phase A or phase B, the piezoelectric effect is different, minus plus. So there is basically in that case a competition. So at a given pump power, the piezoelectric effect, you can show, I will not detail that, but it's a nonlinear response at a given time. The Denver field can saturate or at a given pump fluence, at a given electron hole per concentration. And so this piezoelectric effect, this is just amplitude, but it's negative. So you just have to add the plus, that linear response, it's deformation potential, and minus that piezoelectric effect. So there is at that point just a competition between the two mechanisms. Said differently, this is exactly at low fluence, this is the piezoelectric effect that dominates, and high fluence, the deformation potential. And there is a given fluence where nothing nearly happens. It's just because of the competition of the two kind of electron hole phonon coupling mechanism. So when you play with piezoelectricity, there is something that you think immediately about. These are ferroelectrics. Yeah. For ferroelectrics, due to the symmetry, inversion symmetry, in that case, you can induce not only longitudinal, so this is wave equation, but you can induce longitudinal and transverse. Yeah. You can induce not only longitudinal, but also shear. And in that case, we discussed a couple of years ago the piezoelectric effect that can, in that case, induce longitudinal and shear motion. And this is, to have shear motion, you have to break the in-plane symmetry. And this is exactly what you can play with a ferroelectric material. And the transverse acoustic phonons, it is also something very interesting because these transverse, either acoustic or optical, hold a momentum. So this is something that is important in the community because this momentum are also related to chiral phonon can be used also maybe in the situation of the conservation of the momentum in the case of demagnetization, for example. So it is important to understand how we can induce transverse acoustic phonon with light. So this is what we did in such bismuth iron oxide. So when we shine light, since this is a polarization, so this polarization indicate that the system is non centrosymmetric. So the force you induce with the light is not isotropic. So there is shear as well as the longitudinal. And when we look at the pump probe experiment, you excite the system, you look at how the function of time, how the transient reflectivity change. If you make Fourier transform, you immediately see these two components, longitudinal and transverse. Okay, the splitting is due to Beer function. I will not discuss it. And this just a demonstration of the generation of coherent acoustic phonon and transverse one in such ferroelectrics. Of course, there are different materials, different situations where you can induce transverse acoustic phonon. So people, there are lots of different works on that, gallium nitride as well, to generate a transverse acoustic phonon in that case of a semiconductor. And we did the same thing for thin films. Yeah, what you saw before, it was for bulk bismuth iron oxide. This is the same thing for thin films, so sample grown by colleagues. So this is the 150 nanometers. You shine line such a thin film, and because of that symmetry breaking due to ferroelectric polarization, if you make Fourier transform, you can get longitudinal and transverse. And what was very important in that community of coherent acoustic phenomena, it's also to know exactly what is the amplitude, what is the efficiency of the light energy conversion into mechanical energy. And to do that, it's important to make X-ray diffraction, because with X-ray diffraction, you can have direct access to the strain, which is the variation, relative variation of the interatomic distance over the equilibrium distance. And of course, as you probably know, this is the Bragg law. People apply this Bragg law for time domain diffraction. So in that case, you use femtoseconde light pulse that induce different phonons. And by using the X-ray diffraction, you can come back. Yeah, you look just at how the Bragg peak shift, and then you measure that variation, and you come back to the strain. And we did that for bismuth iron, so nothing new, except the fact that we developed a methodology to measure the shear. If you look at the cubic symmetry here, yeah, if you have a shear stress, you see the red interplanar distance will be different than the blue. In a cubic symmetry, 101 is equivalent to minus 101. But if you have shear, you can break that symmetry. This is exactly what we analyze to get back the shear. If you put tensor on that, you can immediately show that the variation of the interplanar distance, yeah, is related, of course, to the longitudinal, so how the out-of-plane motion evolves as a function of time, but also to the shear. But they behave differently depending on the plane, minus 101 or minus 10 or 101. So if you make two measurements, finally, you measure two Bragg peak, and then you combine that two measurements, and you can come back to the longitudinal and the shear stress. And so we did it with Claire at Soleil at that time. And recently we moved to Max 4 in Sweden, to Lund. And this is the typically experiment we can see. Yeah, this is the Bragg peak. Yeah, this is a Bragg peak. And in red is how the Bragg peak change as a function of time. So, so the question is, you see, when we saw first that's Bragg peak evolving, so okay, let's say two Bragg peaks. So there is a phase transition. No, it's not a phase transition. if you remember, finally, that part is just to the fact that, as I told you, when you shine line a solid, there is specific spatial distribution of the strain. There is a bipolar strain pulse. So there is one part which is a tensile and one is compressive. And this is when if you look at how the Bragg peak, that one changes as a function of time, you will get that variation as a function of time. And that one, you get that one. And this is exactly consistent with the model that we discussed before. Yeah, this is if you remember, if you shine line a solid, you emit such a bipolar pulse. So there is a tensile one and compressive one. This is exactly what we measure. So with X-ray, we can somehow reconstruct the profile of the light-induced strain in that solid. So, and what is interesting that we did it for that Bragg peak, but that one is not equivalent. Why? Just because, so it's a bit technical at that time, but if you combine both measurements, the difference between two Bragg peaks are just due to the presence of the shear strain. So finally, by making two measurements, you can reconstruct the longitudinal one and the shear one. Yeah. So this is exactly, finally, the picture, I can go directly to that one. When you shine light, there is first expansion, there is a shear. After a given time, the relaxation or longitudinal, what's just not relaxation, it's just propagation of longitudinal strain. And the shear is partially refracted and transmitted to the surface. And then step by step, you can reconstruct how the unit self as a function of time evolve thanks to that two measurement of the Bragg, measurement of two Bragg peak. So basically, this is this is a thin film, ferroelectric films, and we have solved how, not only as a function of time, but also as a function of space, which is very important, how the unit self evolve in such a thin film. And from the physics point of view, what is interesting that if you consider that there is a strain pulse that can current phonon wave packet that propagates, there is two components, longitudinal and shear, and this induce a modification of polarization, ferroelectric polarization, which is just related to the current. So probably this that has not been measured, but we are combining THz experiment. We are combining such experiment with THz experiment just to detect that transient of the polarization. So just to finish, I would like to tell you a few words about THz excitation. So I told you this is spectrum that you know now. You are always, for semi-infinite system, always limited. It's nearly very difficult to reach THz. Yeah, because it's nearly impossible to deposit energy only on the surface. Or you can get it if you have, let's say, graphene layer. It starts to work. You have very small layers, like a Dirac, and then in that case, you can shift that frequency to the upper frequency. Yeah. Another way is to confine. That's basically the case. You have a resonator. Yeah. So if you have a resonator, in that case, you can select some frequency in the spectrum you induce by light. So that works. Yeah. The other way is to use two superlattices. Yeah. As you know, superlattice is just artificial, materials made of AB, superposition of layer. And then in that case, instead of having such two dispersion curve for acoustic phonon for each part, you have, let's say, an average mode folding. So in that case, you can couple light directly with the zone center mode here and generate, because there are different absorption of the light, which is not the same for AB. So you select perfectly a given frequency, which is usually the zone center one. This is a bit complicated. This is the dispersion relation. Of course, superlattices are known for 80s. Yeah, are known for 80s. People have built lots of different superlattices for electronics, for, let's say, Compton cascade laser are superlattices. Yeah. And for phonon heat transport as well. Yeah. And in the let's say bit more than 20 years ago, people did it also with pump probe experiment, and they perfectly shown that it is possible to generate nearly THz experiment thanks to the mode folding. And we studied recently the oxide are a bit different than semiconductors. Why? Because there are polar, elastic, ferroelastic, or even ferromagnetic or antiferromagnetic orders. And this can give rise to different bond folding, as I will show you, mode folding. Basically, that superlattices people have for oxide have shown that the bond mode folding, when they shine light, yeah, and this is this is a metallic oxide that absorbs quite well. Yeah? So this is a nearly a large band gap of oxide. So in that case, when they shine light on that system, there is, let's say, a selective excitation of that mode. And this is exactly what people observe in X-ray diffraction, for example, time-resolved X-ray diffraction. That works well. And we did it. We studied recently such oxide, which is BFO, LFO. LFO is lanthanum iron oxide. Yeah. And we did pump probe experiment. Yeah. So when you do that, that superlattices here, so you get such a signal. There's a rapid increase of signal due to the creation of electron-hole pair and superimpose. There are different oscillations. That oscillation at large time scales just to the fact that there are phonons that emitted. So you get just the Brillouin component of the substrate. But if you look at the short time scale, you see such a signal like that. Yeah. And you have two components, 1.2 terahertz, 0.7 terahertz. What I forgot to tell you, that's, of course, if you play with the thickness of the superlayer, yes, I mean what we call the gamma, of course, you can tune the frequency. This is what also, which is interesting in superlattice. And so we did a phonon spectrum calculation, and in the phonon, we detect, sorry, that does not appear well. That one is what we expect. It works quite well. We expect that one that comes from just the mode folding. Yeah. But that one, we did not understand where it comes from. So by looking at the structure, this is the electron diffraction image. So in the Fourier domain, it's the reciprocal space. This is the Fourier transform of the unit cell. But if you look, there are super orders here at a given point in the Brillouin zone here. And that shows you that there is a super order. It means finally it's not A, B, A, B, it's A prime, B, A, B, I prime. So there is doubling. There is a doubling of the supercells. And this has quite a consequence. This has also been observed with Claire by X-ray diffraction. That superstructure here has been observed as well by X-ray diffraction. And finally, it comes from the fact that if you take into account that the system is a ferroelectric, the ferroelectric order, if you look at that, is not the same from two neighbor BFO layer. Yeah. And in that case, it induced the doubling of the superlattices. So we have, let's say, a double mode folding. That's the way as we explained that situation. Okay. I think it's time to now we like not just to make a short summary. So I discussed the photogeneration and photodetection of acoustic phonons. We have shown you different examples for semiconductors, some situation about ferroelectric materials, and just rapidly about the terahertz acoustic wave. So what I shown you, that's finally with light, yeah, we can induce compression, expansion, or shear strain. So we finally, if you understand properly the electron, because in all situations I discussed, we have a creation of electron-hole pair. Yeah. So this electron-hole pair induce deformation potential stress, or can screen electric field, or can induce a Denver field. Each time we have a creation of electron-hole pair. Yeah. So, but selecting the material of the symmetry, so you can really control the kind of the different strain in the solid. Of course, if you combine optics and X-ray, you can get the absolute value of the strain you induce. Yeah. And with superlattices, finally, our recent work shown that finally you can play with the mode folding if you consider that the superlattices are not simply just a superposition of chemically different layers, but due to long order ferroelectric organization, you can have a double mode folding. So today I discussed optical pump probe, this X-ray. So recently we also had something I did not discuss, but we can analyze the terahertz emission. Terahertz emission is just related to the transient of the polarization. So this is what we recently obtained during the PhD of Zenab. And we have a single sample. We now combine all kind of measurement to really understand. As I told you, you can generate lots of things, but what do you see exactly? It's a question I ask you. Depends a lot on how you see the dynamics you want that you have generated by the light. So some perspective, of course, nonlinear phononics, because I discussed phonon. Nonlinear phononics, this is something very interesting. So lots of work has been done by Cavalieri's group, Alaska, Subedi. So these are very interesting. And with phonons, as I briefly mentioned, we can also use different, because a phonon can modify the interatomic distance. So you can modulate different orders, like magnetic orders. So this is what my colleagues, Marwan and Lucy, are working on quite recently. Okay, so I would like to thank you again and thank all my collaborators and colleagues for this finding and discussion. Thank you for your attention.
Thank you for this introduction into the world of phonons and how we create them and the interaction with electrons. So we have time for questions. Who wants to start?
Can we induce torsion? Yeah. Yeah, I would say.
Can you induce torsion with light?
Yeah, that's a good question. This is related. Okay, slide. Special. I think torsion will lead to relation to the shear motion. So you are here. But that case, so if you want to induce torsion, it's exactly the same way that when you create a singular polarization with light, you combine two transverse electromagnetic. Okay? Just plates, like the ordinary for them, like the water plate wave. So in that case, if you are able to generate two kinds of transverse acoustic wave, but in two perpendicular polarization, you control the phase, then you can create, say, a circular transverse, circular strain. So people know how to do that with, say, even in general processes. Right. Many people just discuss chiral phonon. What are chiral phonon? Just you cannot generate new phonons in the solid. So chiral phonon is just a combination of two transverse acoustic. That's all. Yeah. But what is much more complicated is they have to control the phase of these two transverse acoustic wave to induce what you mean torsion. Torsion would be just a circular. A strain with a circular component. Let's say orbital momentum. Yeah. This is what that was your question? Yeah.
And in relation to this question, in all your excitation, you don't describe the effect of the polarization of incoming light.
Yes, you're right. In that case, it is not important. I would say when you are in the situation where you have above band gap excitation, we create electron hole. Okay, the light polarization is important in the case of birefringent material, because the light polarization can tell you that you are absorbed, let's say, along with, let's say, either ordinary or extraordinary axis. Okay, so in that case, that can give rise to different, let's say, concentration of electron hole per you have created with light, because you do not excite the system the same way. For the light polarization, of course, I would just like to come back to that situation. The light polarizations will be important to define the quantity of the electron hole pair you have created if it's birefringent material, okay? So that will govern the value of n. The value of n will also control the value of the temperature, because if you absorb more, you will heat more, yeah, okay? The same way, because the transient electric field, as I explained to you, is also related to the quantity of electron hole you have injected to screen the field. Okay, so always ordinary external. But in that case, if you are below band gap, it's not written like that here, but these two quantities are tensorial. So for electrorestriction, which are also brilloint, it is important. If you pump, let's say, you can, if you, if you turn the polarization depending on the symmetry, yeah, the electrorestriction tensor, it is for sure dependent here on the light polarization. So this is important. I would say mainly the light polarization is important with, let's say, below band gap excitation when it is not resonant. And if you have above band gap excitation, it's a bit usually less important for acoustic point of view. Of course, if you excite optical phonon with Raman tensor, yeah, in that case, it has some importance, yeah, for the light polarization.
Another question?
Generation if you excite in the bound state, because of the terms that you described, what remains?
Is your question referring to deformation potential?
Yes.
Yeah, that very simplified sketch. Yeah, of course. So deformation potential. Finally, this is written for, let's say, current acoustic phonon, but you can have also the same situation for optical phonon. Of course, the way you excite electron, yeah, in different bands, yeah. Sometimes when you shine light, you induce very different interband transition. So you can populate different valley, okay? Sometimes what you observe is just the consequence of the contribution of different, I would say, of different deformation potential, just not only one. Yeah. So because that Grunayson, electronic Grunayson, depend on the K vector where you put electron. Yeah. So your question is about. Yeah. Okay. In that case, yeah. If you the same as a quantum dot, if you have very well defined electronic level where you can populate, yeah. In that case, yeah, it's more easy to relate the acoustic phonon, yeah. You observed, you have generated to the electronic level you have populated. Yeah. Okay. So, and I think it has been done, but in that case, for exciton, probably you have. So, yeah, for exciton, what is interesting that you can really well control. If you are at quite low temperature, you can really well control the electronic level and populate this electric level. So after that, if you know exactly the deformation potential related to that level, then you should understand which phonon you emit. But again, the spectrum, you have to take care about that. The spectrum of the phonon you will emit, even if you populate the quantum dot, will not only depend on the energy level you populate, it will also depend a lot on the spatial distribution of your quantum dot. Yeah. If you have just a quantum dot on the surface, or the spatial element is very important as well. So this is not only the time and the electronic level. Yeah.
Okay. So I have another question. We share. You mentioned rapidly van der Waals bond strength, yeah, being tested. So there is a lot of excitation about 2D materials, which are, yeah, so with van der Waals interaction between the layers.
Yes.
So what have you already tried such materials, or do you know such studies of them? What does it reveal?
Yeah. Yeah, I have one example I can show you. This is something that I did not discuss today, but I can show you one example. For example, a couple of years ago, sorry, so I have to accelerate. We look at such van der Waals interaction in the assembly of nanoparticles. I will show you, sorry. Okay, I should arrive soon. for that. So basically, this is one example. We look at assemblies of particles like that. So the material is made of what? The material is just made of just assembly of particles like that. Yeah. So deposited on surface. Yeah. So you can, with pump probe, induce some, so basically there are particles of 4 nanometers. Yeah. So they are what's like a supercrystal. So you can also induce some current acoustic phonon such layers like that. So these gold particles are connected by, let's say, covalent or van der Waals bonds. And by just looking at the propagation, yeah, at the propagation of this current phonon, so you can, so the signals are quite complex, but to simplify them, you can measure the time of flight of current acoustic phonon in such a system like that. And the time of flight is related to the sound velocity, and the sound velocity related to the stiffness scale. So by looking at how this current phonon propagates in such nanostructure, you can measure directly the bond stiffness between particles. This has been done. We did it as well.
It's a super super
Yeah,
crystal.
but basically, you can do the same thing. We just have so these 4 nanometer particles, but in the situation we have 2D materials, yeah. So you have just a layer. So on the surface, you have such a bond stiffness that connect the 2D materials to the substrate, yeah. And you can induce vibration of that 2D material, and then you come back to this van der Waals interaction. So like you just induce mechanical oscillation of the 2 layer, yeah. So that works quite well, yeah. I mean, the only main issue is that finally, if you have 2D material and if the substrate does not, I mean, let's say this has a thermal conduction which is too low, then you burn the sample. But okay, just heating management. But the idea is really that situation. We did it. I have no slide about that, but we did with, let's say, you can do it with graphene. Yeah, people did it with graphene layer, and they observe this oscillation. Yeah. The oscillation. I have. Well, okay. What I can show you as well? This is, you can modify the nature of the bonds between either the film, the 2D materials, or the nanoparticles, and you can measure it. Yeah. It's, I would say, quite simple. Maybe it's more easy to shift directly to the slide, but we have there is a review I mentioned in the beginning by Fabien Viala. Up. That review. Yeah. So this there is a review if you're interested in. They look at van der Waals films. So they look at basically that pump probe experiment, and they induce films ringing, and by looking at the vibration frequency, they can come back to basically the bond stiffness, I mean, the nature of the interaction between the 2D materials with the substrate. Okay, and lots of things. I did not mention that, but there are now 2D materials that are piezoelectric. There are new magnetic state as well. So people are looking at that. And recently, I saw a paper where they discussed the shear current phonon relation between that's dynamics and the magnetism. But yeah, this is one review, but you can find other paper. So from the physical point of view, nothing very complicated, just a resonator that is induced by light.
No more questions, you know? Okay. So maybe we thank the speaker again.
Thank you.
We check the no question on that.